So now let's look at another way of analyzing how well a mechanism will work. We're going to talk about transmission angle, and this is basically saying how close to the dead center condition am I, and the farther away we get from the dead center condition, the better the mechanism operates. So this is described with the transmission angle. So as I mentioned, as we get near that dead point condition or that dead center condition we talked about previously, which you see on the right here, when those two links are collinear, we have very poor force transmission. I take my mechanism, and now if I'm trying to apply a force to this output link, I get very poor transmission from my input link to my output link. Now, the farther away we can get from that position, the better I'm going to have force transmission. And we find that the best is actually when I get a 90-degree angle between my coupler and my output link. That is our highest force transmission, or the highest transmission angle. So let's define this a little bit more. The transmission angle here, often given the symbol gamma, is the acute angle, acute being less than 90 degrees, acute angle between the absolute velocity of the output link and the relative velocity of the coupler link at their point of connection. So a lot of words here. Let me see if I can sketch this to make it make a little bit more sense. So first of all, the absolute velocity of the output link. If I think about link 2 as the input and link 4 as the output, I can have a velocity vector right here, and this will be the velocity of point C. And then I can have the relative velocity of the coupler link at that point C. So this is the velocity of point C relative to B. So this would be heading down this way, which is perpendicular to that. So that's the velocity of C with respect to B. And now this transmission angle, this is the angle between the two at this point of connection. So right here, this angle, this is gamma, that is our transmission angle of the mechanism. So you can imagine that as I go through the range of motion, this transmission angle changes. The closer I get to this dead point condition, the smaller the angle gets. You can see that over here I've got these velocity vectors would actually overlap each other. And in that case, my angle goes to 0 and I have poor transmission. So this is really how well do we transmit force from the input to the output. Now let me kind of lay this out as far as what would be acceptable conditions, what would be unacceptable. So here we have really a table of worst to best transmission angles. So let me start off with the left column here, which will be a pin-jointed mechanism. And first of all, the worst case would be 0-degree transmission angle, which would look very much like that dead center condition that we just had a moment ago, where I've got an input link over here, and then my coupler and the output link are collinear, so something like this. And in this case, if the link on the left is the input, I have 0 transmission angle, and that's the worst case. The very best case condition would be where I have something with my input link, and then the output and the coupler link are at 90 degrees to each other. And in this case, I now have a perfect transmission angle. So you can imagine that I've got a velocity here of the relative velocity vector of the coupler, and then a absolute velocity of the output link, and that's where I have a perfect transmission angle of 90 degrees. Now, ideally, I want to be keeping my transmission angles above 30 degrees for pin-jointed mechanisms. So I can kind of shade this area in up here and say, I do not want to be working up here. These are not usable. Now, how about slider joints? Well, slider joints typically have a little bit more friction than a pin joint. So we have to restrict this operating range a little bit more. So let me first of all start off with what a transmission angle looks like for a slider. So my worst case condition, I would basically be trying to push, so if I've got an input link, I would basically be trying to push the slider block into the surface that I'm trying to have it slide on. So in this case, I would have a 0-degree transmission angle. I've got the velocity of the slider also acting in the same direction as the relative velocity of the coupler. I have 0 transmission angle in that case. The very best case is where I'm trying to just push the slider right along its axis of travel, so something like this. Input link on the left. And now I have 90 degrees between the velocity of the slider and the velocity of the coupler with respect to the relative of the coupler. So this would then be my 90-degree transmission angle. So with the slider joints, I basically have to restrict this somewhere around 60 degrees and say anything less than 60 degrees I really don't want to be operating because I have too much friction in a slider joint and I will cause the mechanism to bind up. So this is really limiting the operating range of many mechanisms, and There might be a little bit of wiggle room with some of these in that maybe we could get down to a 50-degree slider transmission angle, maybe 20, 25 for a pin joint. But you do find that mechanisms that are operating in those low transmission angles do work poorly. You certainly do notice it. So, what are some limitations of using the transmission angle? Because first of all, it is purely a static analysis. So we're just looking at the mechanism as it sits, not thinking about any of the dynamic forces being applied to it, how fast is it moving. And sometimes the dynamic forces can be quite considerable. If you think about an internal combustion engine where we have a crank slider mechanism, there we're passing through these zero transmission angle conditions, but because of the dynamics and the inertia of the flywheel, we can move through those without any problem. It also neglects gravity. Very often we have a lot of mass on the coupler or one of the other links that might help us through this low transmission angle area. And it assumes that the coupler is a two-force member. So perhaps the coupler has an external force applied to it. That might help it through the poor transmission angle areas. So it's not a perfect measure, but it is a measure that helps us figure out, is this mechanism going to operate or not? And it's based on geometry, so it's very fast to do an analysis of a mechanism. Now, with that said, there is another tool that you can use to do a little bit better job of analyzing how well a mechanism will work. And this is called the joint force index. So the joint force index is basically looking at what is the force at each one of the joints, so each one of the pin joints, and comparing that to the external load on the mechanism. So let's say that we're pushing some external load that might be 500 pounds. Well, we then compare that to each one of the joint forces, and ideally we would like each one of the joint forces to be under 1,000 pounds, or 2 times the external load. So this IJ here that we're looking at, this is the force between each one of the links I and J, and hence the joint force. So an alternative way when our transmission angle is not realistic based on some of these limitations that we just discussed. So again, a tool, but not a perfect tool that helps us decide if a mechanism is going to work well or not.